we have to convert the strings to NumPy arrays to make that work, but that's pretty fast. And the code should be pretty fast too. Let's have a look. Okay, so that's pretty fast. Hello and welcome to Big Python. In this episode we're talking about fuzzy search. In this video we're first going to look at how you can do something like autocomplete for a set of strings in Python using libraries. And in the second part we're going to explore how that actually works, and we'll try to make our own fuzzy matching library. So let's get into it. What I have here is a set of names of places and cities in Britain. It's about 60,000 items. And I can search them using this input, and it should find places even if I don't type it exactly correctly. So something like, yeah, as you can see, it finds some matches based on that. So let's try searching for something that probably isn't in Britain, like so as you can see, I can search the list in pretty much real time. It takes about 1/10 of a second to search, and it gives me nice results of strings which are kind of similar, but not exactly the same as the one I put in. So how can you do that in Python? As with most things, there are already libraries for this fuzzy matching, or also called approximate matching in Python. One of them is fuzzywuzzy, which has been ported to different languages. So you can use it, for example, from JavaScript as well. If you want more performance, you can use rapidfuzz. That's what the first example with a city uses. And if you want to stay just with the standard library of Python, you can use difflib. All three of these libraries have a function like this, where you plug in two strings and it tells you their similarity as a number. Here that's 93%. And when you can do this, you can of course extend it to multiple words so that you can find the best match among a given list of words. That was the first example with the cities. Well, the question is, how does it actually work, and what do these numbers exactly mean? The answer to that can be a bit tedious. In the first example with the cities, it uses a function from the library called w-ratio, which uses different criteria to compute the number. But basically it's based on something called edit distance. We're going to have a look at that in just a moment. And we're going to build a solution from scratch, not using the libraries, but just Python. And hopefully in the end, we'll have something similar to the first example, which is a fuzzy search in the 60,000 strings in quote unquote real time. The library from the first example is actually implemented in C++. So we'll have to use some tricks to get to that level of performance. Since we are talking about approximate string matching, of course the usual string comparison is not useful, because two strings are equal only when they are exactly the same, while what we want is that number that will tell us how similar or not the strings are based on their content. So let's have a look at some simple ways you can compute such a number. Well, one popular choice is something which is called edit distance. You can think of that as if I was writing one of the words, and then how many key presses would I have to do to convert one of the words to the other. So like how many letters do I have to delete or insert or so on. And based on what exactly are the editing operations, there are different measures of this type. We'll be looking mainly at this one, which is the most common one. It's called Levenshtein distance. But there are other possibilities as well, depending on what kind of text you have and how long it is. You may want to look at stuff like frequencies of letters and words, substrings, and so on. But in this tutorial, we'll be looking at the edit distance. So let's have a look. So the simplest editing distance is called Hamming distance, and it has just one operation, that is replacing a letter at some position with a different letter. So here we have distance 1, distance 2, and if you have strings which have different lengths, that's usually not even defined. One reason for this is that it was created in context of error correcting codes, which are schemes where you have like a block of bits and you want to be able to detect some number of errors or even correct them. And you always have, it's a block oriented, so you always have the same number of bits every time. So that's one reason. And the other reason is that it doesn't really work either way, because when you have something like this, where you have a shift in the sequence, and then the Hamming considers this like individual errors at every position, instead of like here I've deleted the space and here I've inserted the space. So that's why it's not that suitable for text. We'll have a look at the Levenshtein distance, which can do this in just a moment. But first, let's have a look at the implementation for this. It's pretty simple because we can just sum the letters that are different. And let's have a look at how it works with the cities. So let's try something. And as you can see, it kind of works. It doesn't really suggest any different length because it can't, but somehow it works. When I try something shorter, yeah, it doesn't. It cannot find the right answer. Let's have a look at the Levenshtein distance, which is more advanced now. Well, the basic idea is the same, but it adds more operations. So instead of replacing one letter with another, we can also add letters or delete them, which can work like this. Let's say you have moon, and you want to make moon out of monsoon. Well, you can skip the first two letters, then delete 3 letters, and keep the rest. Which is, in this case, it's the least number of operations you can do. So it's the distance. And it also is some sequence of the edit operations. We also talk about cost, so that every operation has some cost. In this tutorial, we'll consider all operations having the same cost of 1. But you could also weigh them differently to get different results. So the question is, well, how do you do that with an algorithm? With the Hamming, it's really straightforward because you just iterate over the string and look at the letters at the same position. But now you can have at every position you have like 3 possibilities what you can do, and it's not really obvious what you want to do to get the minimum number of edits. So looking at something like this, we know that we should delete this space, and that's the only thing that we need to do. So the distance is 1. But if we instead use the substitution operation, then we would replace the space with the D, which would misalign the sequences, and we would get errors all over here. So it would be distance like 7 or something, which is not the distance, is not minimal. So how do we implement this? Well, one way is to just try all the possibilities using recursion, which is way too slow to be actually useful. But it can be optimized using dynamic programming, and the result is called the Wagner-Fischer algorithm, and that's what we're going to look at in just a moment. There is also an alternative approach using finite automata, which has some very cool properties, but unfortunately it would be way too long for this video. So let me know in the comments if you'd be interested in that. So the Wagner-Fischer algorithm. If you've never used dynamic programming before, it may look a bit daunting, but don't worry. It just builds up the result based on distances of shorter strings. We have a table which we're going to fill in, and at the end we'll read the result from that. Let's have a look at an example. So let's say you want to compute the Levenshtein distance for 2 strings, cat and wildcat, using the table approach. So first you create a table that has 1 row and 1 column more than the length of the strings. And then we'll fill it out, starting in the upper left corner. And then in the lower right corner, that will be the minimum edit distance, or the Levenshtein distance. How we can think about this table is that it's partial results. So this is like if A was just empty string and B was just empty string, then the distance would be 0. Well, and if A was empty string and B was just the letter W, the distance would be 1, because we would have to delete the W to get the empty string, and so forth. So if A was empty string and B was WI, then we would have to delete 2 letters, or 3 letters, 4 letters, and so on. And the same thing actually applies on the other side as well, because if B was empty string and A was like C, then we would have to insert the C into B to get it the same. So it's like this. If A is cat and B is empty, that means we have to insert 3 letters to make B into cat as well. So let's have a look at some ways you can get cat from wildcat and how that translates into the table. Well, one first and really stupid way would be to, let's say you have your cursor here. So you would write cat, So we would insert cat to the beginning and then delete the rest, which would be like this. So we're inserting cat. So we have the cost 3 here. And then you have to delete all the letters. So here you would have cost 7 plus 3. So that would be 10. So that is not the distance, because the distance is the minimum cost. This is just one possible set of editing operations that has a rather large cost. So let's try something that to decrease the cost a little bit. Well, instead of inserting some strings and deleting them, we can just replace them. So we can go like this. So we will override the WIL with cat. So that will be moving like this. And then we will delete the rest. We don't have any matching letters here. We have to override C with W, A with I, and so on. So here we have cost 3, but we are way further down in the string. So now we have 3, 4, 5, 6, 7. So that would be 7, which still isn't the right answer, right? Because what we should do is this. We should delete the wild, and then we have cat and cat lined up, so we can go down. But as we go down, we don't actually increase the cost, because we're substituting C for C. So that's for free. So here we have cost 4 because we've deleted 4 letters, and then we don't do anything. We just skip them. So here we have 4, which is actually the correct result. So let me show you how the filling of the table actually works. So here we have a blank space, and we'll go row by row like this. So we're here, and so we can have three options. So we can either we have C and W, so we can substitute. So we take whatever was here and add 1 to it, so that will be 1. Or we can insert the C after the W. So we will take whatever was here and add 1, which would be 2. Or we can delete it, which is here plus 1, so that would be 2. So out of those 3, the best thing is to take this and replace it, so we get 1 here. We can take this and add 1, which would be 2. Take this, add 1, which would be 3. Or take this and add 1, which would be also 2. So 2. Okay, here I believe it's 3. Here it's 4. And here it starts to get interesting, because we have C and C. So we can take this and add 1, which would be 6. This add 1, which would be 5. Or this and add 0, because the C and C actually matches. So the best thing is to take this. And as you can see, this is the correct path in the end. So I'll just quickly fill out the rest, and let's see how that looks. So I've filled the table. That's the final state. And as you can see, we got the correct answer just by filling the table. So that's how the Wagner-Fischer algorithm works. So let's try the same thing in code now. We should have the same result as before. Yeah, cat and wildcat. Here's the table, and the result is the same. It's 4. Oh, well, how does this simple Python code stack up against the libraries? Let's compare it with the Levenshtein library, which implements the Levenshtein distance in C. And as you can see, it is significantly faster than our Python. It's about 2 orders of magnitude. Here it takes nanoseconds, while for us it takes microseconds. Well, what does that actually mean? Let's try the cities example. So let's search for London. As you can see, it takes about a second and a half, 2 seconds. Yeah, it's not really real time. Yeah, I mean, the results don't look too bad, but it takes too long to be really a real-time search. So how can we improve this? Well, I want to show you one general way of addressing this. One way would be to use something like Cython or Numba to basically compile the function closer to machine code and make it run faster as it is. But we can also reformulate the problem and say that we want to compute a distance not just to one string, but to a list of strings and get a list of results. Let's have a look at how that could work. So what we had previously was basically we had one table for 2 strings. So let's say that was cat and this was hat. So we put that into the algorithm and it created one number. So let's say cat and hat, that would be 1. But with the vectorized approach, we create many tables and compute them at once. So like we would have cat, but here instead of having just one table, we would have like many tables. So let's say that's like hat and rat and car. And we would process them at once. So the result will not be just one number, but it will be a vector of numbers. The trick in this is that we can very quickly evaluate all the operations here, because here we're just doing like sum of 2 numbers or a minimum of 2 numbers, and here we're doing sum of n numbers and minimum element-wise of n number vectors, which can be done very efficiently. And also it gets rid of the dependencies here when we compute it. Because when you're filling out one cell in the table, it depends on the cell before it. So you cannot just fill the whole line in parallel. But when you have many independent tables, then you can work on that one element in all the tables at once. So that's why it is so much faster. In terms of Python, thanks to NumPy and its broadcasting rules, the code is pretty much the same as it was before. The table gets one additional dimension, that is the stacked tables. Instead of minimum, we use NumPy minimum, but the code overall is pretty much the same. Of course, we have to convert the strings to NumPy arrays to make that work, but that's pretty fast. And the code should be pretty fast too. Let's have a look. How it actually works with the cities. So let's try. Okay, so that's pretty fast. Yeah. Yeah, it works. The results are not the same as the fuzzy matching from the first example, but I think they're usable and it's really comparably fast, which is interesting given that we're just using Python and not C++ modules. Well, for one last test, let's compare the performance to the Levenshtein C. And as you can see, for the first Python implementation, it takes about 5 seconds. With the vectorized version, we're getting to 150 milliseconds, and the C is done in 18 milliseconds. So we're only about 10 times as slow as the C, which I think is a cool example of what you can do with Python if you just optimize it a bit. Thanks for watching the Fuzzy Search video. If you have any questions or comments, feel free to leave them below, and I'll catch you next time on Big Python.